Last time. For students sitting in the back, can you hear me? Okay, great. So remind you if any time microphone doesn't work. Again, I want to clarify some question asking the email during the weekend. So first thing is on the one UFL, you probably see like final exam scheduled. That is automatically generated for every class. We don't have final exam. We only have the third exam, which is December something. Check Canvas. We only have the third exam, but we don't have final exam. Ignore the thing schedule on Canvas. So you are pretty much free after exam 3, the third exam, free from my class, of course. And of course, I assigned a second project during the weekend. It's due the Friday. I think that day is a reading day. Yes, that Friday night. But of course, you can always finish that project early. And if you finish that project early, you are pretty much free after my third exam. So that is some of your concern. And also for some of your concern about the exam 2 grades, should be fine. First thing is that, of course, what I did is I added 10 points for everyone. I extended 10 minutes for everyone in both classrooms. And also said that if it's a mistake that made by majority of students, I would consider it's my fault because because I didn't explain the thing clearly enough in the classroom, which caused majority to make that mistake. I will adjust grading rubric. So that is the thing I will do. And also, as I said, if the average is lower than 80, I will curve the average to 80. And also, probably I don't remember if I said that in the first class when I talked about syllabus, but for all my lecture type of class, if the when I finalize grade, if let's say my target is we should have more than 40% of people have A in my lecture type of class. So let's say if we have 20% of students in the end get A, then I would shift the whole grading scale to make it is at the 40%, and that is A. And of course, the whole grading scale is shifted, including A minus, B, everything. So exam itself sometimes can be easy, sometimes can be difficult, but I'm trying my best to make sure that your final grade will be reasonably reflect your effort in this semester. So don't worry too much about one exam or kind of thing. So everything should be fine. But of course, you need to work hard. This is not 100% students get A in my class. So that's one thing you need to know. And we finished the CST element, triangular element before the exam. And today, start from today's class, we're talking about quadrilateral element. And also want to say that this semester is about 1 chapter slower than last semester. If you had friends who took my FA class before, they may say that we'll learn more things. But I personally do not consider it's a bad thing that we are slower than the previous semester because this I actually prefer in this way because this is a more interactive class because you guys ask questions which I'm not intentionally make class slower or faster because when students like super quiet, no question asked during class, I can go very fast. But if there's a lot of question, which is a good thing, the class tend to be slower. But I actually prefer to do it in this way because when you guys actually starting ask question when it means that you guys start understanding and thinking as an actual engineer. For example, I remember there was let's say for this one, I remember one student asked like, okay, why there are like zero stress when there's only force applied in X direction, why the strain in the Y direction is 0, but the stress is non-zero. So it means that you guys actually start thinking about the physical meaning after behind the numbers. That is the thing that I actually want to see, guys. It's not about numbers; it's your understanding part. So keep asking questions in the class. That's what I mean.
Time is spent on when we're going to get ready to back for the project and the exam.
What I asked here to do is all the assignments should be graded within 1 week. That of course they didn't exactly follow that rule. But I would say that I will try to post the grade on Wednesday and bring the exam back on Friday because we don't have class on Wednesday. Yeah, but I need to keep talking to TA. And for the project, I will try to make them finish grading before the weekend. How about that? This Wednesday. Exam was last Wednesday. Monday? It was Monday? Already? I need to talk to them. Sorry, I thought it's Wednesday. I will talk to TA. So, any other question?
Maybe last Wednesday?
No.
What? Zoom.
I have. Yeah. Yeah, it's one abacus replaced winter class. Yeah. And of course, we need to schedule another class that, yeah, I will do later. So in the introduction of plane stress part, I remember that I show the pictures of modeling 2D plane stress situation using triangular element and using the quadrilateral element. Remember here, we had quadrilateral element model plane stress, we had triangular element model plane stress. And we have done everything with this one. Now we start from this one. And of course, the general idea will be still the same. Interpolation, stiffness matrix, KQ equal to F, and the calculus stress strain. So let's start from the interpolation. And again, we start from the general situation. This is chapter 64.1. 4-node rectangular element. Let's assume that we have a XY coordinate and we have 4-node rectangular element in this XY coordinate. And for the starting point, we assume that it's a rectangular element that 4 edges parallel to the XY coordinates. For different shape, we can talk about isoperimetric mapping later, but that's a different chapter. But let's say for now, everything we derive here is based on the rectangular element with 4 edges parallel to our coordinate system. So we define this as node 1, node 2, node 3, node 4. And we can, let's make it mark it here. Four edges parallel. And of course, coordinate of 4 nodes, x1, y1, x2, y2, x3, y3, node 4, x4, y4. And interpolation basically means that if we know the coordinates at 4 nodes, if we know the displacement at 4 nodes, which basically means u1, v1, u2, v2, u3, v3, u4, v4, we need to figure out the displacement u and v at any point within this quadrilateral element. That is interpolation, right? So, and of course, since we already learned the bin, we already learned the bar and CSC, we know that we need to derive shape function. So then we need to get shape function times u1, shape function plus shape function times n2, n1, u1, n2, u2, n3, u3, n4, u4, and we get the expression. So that is the good question. Yes. Thank you for the question. Actually, I will clarify here. That's why I always encourage you guys to ask questions. So here, we need to make sure that it's always this is the first, it's not just counterclockwise. This should be the first node, this is second node, this third node, this fourth node. It should, because our derivation is based on this node location. If you check a textbook, actually, this this is a textbook. There's a minor mistake here. I want, just in case you guys want to read textbook. It say that the first node of element can be arbitrarily chosen. However, the sequence of node 1, 2, 3, 4 should be counterclockwise. This is not exact correct. The first node cannot be arbitrarily chosen. So it has, you can prove it after class. You can like rotate the node and do the calculation. You will see that you'll get different answer. It means that this is not accurate. So I want to emphasize our 4 nodes. The first one should always be here. Second, third, fourth. And of course, in real life application, your node order can be like really in anything. And also the full edge does not necessarily like parallel to the coordinates. And in that situation, there's a different chapter. This is called isoparametric mapping. But here we're starting from the simple situation. We'll talk about that one later. That's a different chapter. So 4 edges have to be parallel to coordinates, and the first node has to be here. This is how we derive the equation. So now our goal is to find the expression u as function of x, y, and v as function of x, y. And pure mathematically, of course, similar as what I said in the CSG element, u and v, they're perpendicular to each other, so they should be independent of each other. And we can do the derivation separately. And for the u, we know that we have 4 information for our interpolation. We have u1, u2, u3, u4. What kind of polynomial should we have? We have 2 variables, x and y. We have 4 information. What kind of polynomial, mathematically, pure math, what kind of polynomial should we have? In the CST, we have 3 information, and we have the constant term, linear in x, linear in y. Now we have 4 information. We add 1 extra term. What that extra term should be? Cubic? Why cubic? Cubic in x or cubic in y? So let's say you said you want to add a 1 extra term and it should be cubic. Do you want cubic in x or cubic in y? That's my question. X. Yes. Thank you. Because if you say cubic, well, first you need to go in order: constant term, linear term, square term, and cubic term, right? You cannot jump to cubic directly. And if you say, let's say constant term, linear term, and then I have square term, but square term you have x term and y. And if you only have one extra term, you don't know which one to choose, because if you choose x or y, it becomes unsymmetric. So the best way is xy, binary term. So let's say we consider we have 4 information, we can have 4 unknowns. Alpha 1 constant term, alpha 2 x, alpha 3 y, and alpha 4 x y term, right? Beta 1, beta 2, 3, xy. This is for derivation part. This should be the polynomial we have. 4 information, 4 unknown, right? And our goal is to write in terms of a shape function. Since we have repeated this in so many sections, so many chapters, I can write it directly. So our goal is, let's say for interpolation UV, for V should we be similar. So for U, what we want is that N1, X, Y, U1, N2, U2, N3, U3, and N4, U4. Starting point of our interpolation and our goal of interpolation. And of course, if you are really into the theory and mathematical part, the textbook has a standard method to derive the shape function, and it's called Lagrange interpolation. So it's basically you derive the shape function in the x direction first, and then in the y direction. It has several pages. Actually, I can show you here. Okay, it's outside. So this is the Lagrange interpolation procedure. I personally do not think it's necessary for this class, because people sitting here, we are engineers, we are not really mathematicians. But if really into this one, you can talk to me during the office hour about this method. It takes several pages. But let's focus on understanding part, how to have the easier way to derive this shape function. Since we already talked about interpolation in 1D, interpolation in 2D, interpolation for being interpolation for CST. And we already know that, let's say in the CST, remember that I said N1 is always 1 at node 1 and 0 at other nodes. N2 is always 1 at node 2 and 0 at other nodes, right? So basically, I wrote for the CST element, Ni, shape function node I, is always 1 at that node and 0 at all other nodes. So if you understand that this is the property of shape function, actually, we can write shape function in a very easy way, because we just want, let's say for N1, we just want to write a function that is 1 here and 0 here and here. For shape function N2, we just want to write expression that satisfies it is 1 at node 2 and 0 on this edge, right? So if we understand the property of shape function, we can write this shape function directly without the Lagrange interpolation. So let's first put the function of 4 edges here first. So on this edge, we can simply write as y1 minus y equal to 0. So any point on this edge is satisfied that y equal to 1. And of course, you can say y2, but y1, y2, since they're parallel to coordinates, they're the same thing. And edge 2, 3, we can write as x3 minus x equal to 0. And of course, you can also write as x2 minus x equal to 0, but x2 and x3 are the same thing. Similarly, we have y3 minus y equal to 0. And this edge, edge 4, 1, should be x1 minus x equal to 0. For any point on this edge, it should be y equal to 1. Any point on this edge should be x equal to x3. Similarly here and here. And now let's say for shape function N1, we want something that is 1 at node 1 and 0 here. So we know that it should have at least 2 components. This one times this one. So basically any data point on this edge and this edge, it can make this term equal to 0 and this term equal to 0. Right? So let's write the shape function. For each shape function N1, it should include term x minus x3 minus x and y3 minus y. It should include this edge equal to 0. So include these 2 terms. How to make it? Now you can see the whole thing, right? And also, I want to satisfy that it's equal to 1 at node 1. So what we can do is that it's basically normalized at node 1. So we can have, right in this way, x3 minus x1, y3 minus y1. Now we check this expression. When we plug in the coordinate at node 1, x1, y1, x1, y1 is equal to 1. Make sense or not? When we plug in the coordinate at node 1, this is x1, this is y1. So this term equal to 1. N1 should be 1 at node 1. And also, when we plug any point on this edge or this edge, it makes this term equal to 0. And also, it satisfies that this is binary term, right? It has x term, y term, constant term, and xy term. So do you agree with me that this term, this is the shape function at N1 at node 1? It makes equal to 1 at node 1 and 0 on this edge and this edge. And similarly, we can do the same thing for N2, N3, and N4. U1. For shape function N2, again, we need to make sure that it is 0 on this edge and on this edge. So we need this term times this term. So we have and since we want to be 1 at node 2, here should be minus x2, y3 minus y2, u2. So in this way, when you plug in x equal to x2, y equal to y2, this whole term equal to 1. When you plug in any data point on this edge and on this edge, it makes the whole term equal to 0. And let's repeat for node 3 and node 4. So what? X1, 3, y1, y3, u3. Six. Y. Y1, y4, u4. Let me show you very quickly. And you can see here, shape function N3, it needs to be 1 at node 3, and it should be 0 on these two edges. So it should include this term and this term, here and here. Any point on these two edges can make this term equal to 0. And to satisfy that it's 1 equal to node 3, you plug in x equal to x3, y equal to y3, this whole term equal to 1. Same thing for shape function in node 4, you need to make sure that it's 0 on these two edges, so it should include this term times this term, y1 minus y, x3 minus x. And when you have plug in x3, x4, y4, this term becomes 1. So this is a shape function n1, n2, n3, n4 based on our understanding.
With the U's replace V's, just like it was in the last version.
Sorry?
I with the 3-node version, the V of XY would be, the same like N1, N2, N3, except times, V1, V2, V3, is that going to work the same here as well?
Yes. Because if you consider, let's say if repeat the whole thing again for the V. So basically now we have Vxy equal to N1, V1, N2, V2, N3, V3, N4, V4, right? And the derivation part is the same. We assume that we have V1, V2, V3, V4. And again, shape function is always the same. N1 should be 1 at 0, 0 at all other nodes. N2 should be 1 at node 2. N2 should be 1 at node 2 and 0 on this. So we can repeat the whole derivation all over again, and you will see that it's the same thing. So this shape function we derive here, it is for U interpolation. It's also the same for V interpolation. You can simply change Vxy equal to N1, V1, N2, V2, N3, V3, N4, V4. Right? There should be no difference in terms of derivation. So there should be no difference in terms of shape function. And of course, if you check connection nodes, you see that the shape function of the CST element, it has a relation to the area of the triangular element. And now, actually, we can easily see that what is x3 minus x1 times y3 minus y1? Let me show you. X3 minus x1. Let me turn off my phone. It's kind of annoying. X3 minus x1 and y3 minus y1 is area, right? It's area. So here is area. Here is also area. This is negative sign, negative, negative, positive. Here, y3 minus y2. This is positive. x1 minus x2 is a negative term. So it's negative area. And the same thing here, this is negative area. So positive area, negative area, negative area, positive area. Simplify this equation furthermore. Let's write it down. So now we have A represent area of our rectangular element. Minus 1 of A. Plus minus 1 of A. We're done. Right. We're done for the shape function derivation. And of course, this is the simplified method for derivation based on understanding. If you want to know the Lagrange interpolation, you can read textbook and talk to me during the office hour. So let's make it clear. This is N1. This is N2. This part is N3. This part is N4. And don't forget that that includes these two negative signs in the shape function N2 and N4, because our standard expression should be N1 U1 plus N2 U2 plus N3 U3 plus N4 U4. So those two negative signs in the N2 and N4 should be included in the shape function. And of course, as Frieden just asked, for the interpolation for V, we can simply write as V x y equal to N1 V1 N2 V2 N3 V3 N4 V4. Any question? In the exam, this will be provided. Shape function, or the shape function will be provided. And to help you visualize this shape function, where is the picture? It's here. So let's say if this is node 1, shape function n1 means if, let's say, if I ask you to use MATLAB to plot the shape function nx as function of xy, so xy coordinate, and it should be 1 at node 1 and 0 on all the other nodes, and including these two edges, of course. So this is n1. Shape function n2, it is 1 at node 2 and 0 at node 1, 2, 3, and of course, including these two edges. And same thing for n3 and n4. Make sense or not? So this is like help you visualize the shape function for our quadrilateral element. And of course, this is standard procedure. And in the CST element, do you remember that we talked about if it point on the node, we don't really need to go through the standard procedure like calculate all the F and B and C and N1 and 2 and 3 and go through all the procedure to do the interpolation. If it point on the edge, in the CST element, we talk about it becomes a 1D interpolation. And I think this one can also help understand like why it becomes a 1D interpolation. Let's put everything in one graph. Let's say this is shape function n1. And we know that n2 is not really in this figure, but let's say if we combine in one, then it should be something, I'm not really good at this. Yeah, imagine. Use your imagination, I don't know how to. So basically something like this, and 0 at 3, 4, 1. And now let's say if it's a point on edge 1, 2, and it cut the whole thing only in terms of this plane. You just imagine you slice this 3D space, and we only have this plane. And what you will see that it becomes, this is n1, this is n2. 1D interpolation. Make sense or not? It's same as what we did in CST. And n1 is 1 minus s, n2 is s. 1 minus means it's 1 at s equal to 0, 0 at s equal to 1, and node 2. N2 equal to s, it means that it's 0 at node 1 when s equal to 0, and 1 at node 2 when s equal to 1. So in terms of a point, no matter it's on the triangular element or quadrilateral element, if it's a point on the edge, we actually do not need to calculate all those shape function and do the calculation. It simply becomes a 1D interpolation, and it's exactly the same as what we talk about in the CST element.
Why the X be a Y?
Sorry, why X, Y, what?
Why X be a Y?
That's a good question. It actually doesn't matter. So the dimension for the edge dimension, I intentionally for the quadrilateral element, this edge length and this edge length does not need to be the same. It does not need to be a square element. It just needs to be a rectangular element that has 4 edges parallel to the coordinates. So it does not to be like 2, 2, 3, 2 and 2 or 3 or 3. Yeah, it can be any number. Yeah, great question. Any other question? So everything we derive here is for, in general, rectangular element. It does not need to be a square element. Yeah. So now, let's write it down for the point on the edge. Is there AC problem in this room? Sorry about that. I cannot control that. Displacement of points along the edge. Only depend on displacement at two nodes of the edge. Yes. A good engineer means that you can work in any kind of environment. You can focus in any type of environment, not distracted by anything. So this is the interpolation part. Of course, the next step is how to calculate strain. Since we have the displacement function as function of x and y, strain is basically we can derive from the definition of strain. Again, it's the same thing as what we did in the CST. Strain in the x direction is always partial derivative of u with respect to x, and the same thing for strain in y and the shear strain. Let's derive the strains here. Normal strain in the x direction, partial derivative of u with respect to x. So again, if you check this interpolation function, these are the four constant terms. These are the four terms has x and y in it. So the partial derivative basically is partial derivative of shape function, right? You cannot derive like the constant term. So we can simply write as, since we have four terms here, the sum of shape function ni x ui. Similarly, strain in the y direction, partial derivative of v with respect to y. And we also have four terms. Ni y vi. And for the shear strain, u y v x. And now we should have 8 terms. Remember in the CST we have 6 terms for shear strain. Now we have 8 terms because we have one more extra node. So from 1 to 4, we have ui plus vi. And also remember in the CST element we have the B matrix, which is the matrix that connects the strain and the degree of freedom. Same thing here. I want to write the B matrix here directly. Since we have the shape function, let's repeat for shape function to put it together. N1 equal to 1 of A x3 minus x, y3 minus y, n2 negative 1 of a, y3 minus y, n3 1 of a, x1 minus x, y1 y, n4 Now let's see how to write this one in a matrix form. So we know that we have strain in the x, normal strain in x, normal strain in y, and shear strain. And we know that there should be a common coefficient 1 over a here. And how many components in this Q vector? How many components in this Q vector? 8, yes, thank you. So it should be U1, V1, U2, V2, U3, V3, U4, V4. And for this matrix, B matrix, I can show you just for one line. You can see that N1x, there's a negative x here, so there should be negative and this term, right? And N2, there's a negative x here, so negative 1 of a and this term. So our B matrix becomes y minus y3, second term 0, y3 minus y, 0, y minus y1, 0, y1, 0. To make it clear. Similarly, for the strain in the y direction, we have 0, x minus x3. So it's similar. So it becomes shape function y. There's y here, and there's negative sign, so it becomes this term. Zero x1 minus x, 0 x minus x1, 0 x3 minus x. For the shear strain, all a terms, they are non-zero. Y3, x1 minus x. Any question? So it's simply derive the shape function in terms of x and in terms of y and put it into a matrix equation form. And of course, this whole matrix we define as a B matrix for our quadrilateral 4-node quadrilateral element. Q4 means 4-node quadrilateral element. I intentionally put 4 here because we could have more advanced element, which is adding extra node at the center of each edge. Then we can have higher order polynomial for the interpolation, and it has better capability of representing more complicated situation. But here is simply a 4-node quadrilateral element, and this is a B matrix. And so this one I can simply write as a strain vector equal to B matrix times all degree freedom vector. Any question? Y and X, good question. Y and X are variable. So it becomes a function of X and Y. Yes, yes. So this also tells the difference of the CST element and our 4-node quadrilateral element, because if you remember in our CST element is purely X, Y coordinates. There's no variable X and Y in it. So it basically means that all the strain, they're constant. And of course, if all the strain are constant, all the stress, they're constant. So the capability of the CST element is that it can only represent constant strain and constant stress. But here, great question, since we had variable X and Y here, it means that it can change. It has, let's say for this term, it means it can linear change in Y, linear change in X, linear change in both X, Y. So it's a more advanced element type to model more complicated plane stress situation. Yes. Any other question? We only have 3 minutes left. I will start the example problem in the next class. Yes, that's purely strain times C times strain equal to stress. That part is exactly the same. Yes.
This might be me jumping ahead here, but like, let's say you had 2 touching, right? So you're putting multiple on one object. Wouldn't you not be able to use this version because one's deformation would off-skew the other one probably from being X and Y aligned? So you'd have to use whatever the next one is. Does that make sense?
Sorry, can you repeat that question?
So like, let's say you had 2 connecting, 2 of these kind of element or this kind of models.
Yeah.
Next to each other.
Yeah.
Wouldn't one's deformation also deform the other, so neither would be X, Y aligned? So you wouldn't be able to do this process?
You can divide a one structure into multiple elements, and then you can do assembly.
Okay.
So the process for, let's say, if you have a structure like this, you can use,
Yeah.
and then you can do the K for this one, K for this one, K for this one, K for this, and then based on how it connected, you can do the assembly. And then in the assembly, you have a big matrix and all the.
No, I get that, but so these are still like X and Y aligned, like you said, it has to be for this version.
Yes.
Wouldn't, like, when this deforms, wouldn't the boundary conditions from the previous one cause the next one to not meet those conditions?
When it's not parallel, then it's chapter 7.
Okay.
It's
So,
as a
so yeah, you
mathematics.
couldn't use this method for
No.
multiple hitting each other because the boundary conditions would cause problems. It's deformation.
It's deformation is after force applied, then it doesn't matter. If the original shape they are still parallel to the coordinates, we can still use this method.
Oh.
And the deformation you're talking about is after force applied, it's general deformation.
Okay, sorry.
That's a different thing.
Yes, okay, sorry.
But if you're talking about the original shape is not already is let's say if the original structure is something like this,
Yes.
then you cannot use this method. Then it becomes the match. Yeah.
Okay. Okay, thank you.
Yeah. But we'll talk about that one later in chapter 7. Hi.
Let's go.
Yay.